we have found that between 80 and 90% of the lakes and streams which have been resampled were measurably more acidic now than they were 20 to 40 years ago. Although methods
and the decline of red spruce are not unrelated items. These may be indicators of problems in our environment, and these may be heralding other events which are taking place about us today, but we just don't know enough about the environment to know what they are. And that these are the kinds of things which will affect everybody. People may ask,
and we can't therefore estimate costs. It's a race against time. Our measures are futile unless the environment is cleaned up. The costs become irrelevant. The loss of these things is forever.
The New England countryside, with its playful brooks, its majestic mountain views, its rustic stone walls running through woodlands and along roadsides. The Adirondack Mountains of New York State, the largest unspoiled wilderness area in the Northeast. The rain and snow are a part of these landscapes. The water they supply plays a vital role in the life cycles of every living organism, from the simplest single-celled plankton to the most complex of creatures, man. But something has gone wrong with our rain, snow, and air. More and more, our rain and snow contain airborne pollutants, such as particulates, sulfates, lead, and other aerosols. These pollutants are transported through the atmosphere and eventually fall to Earth in a process that is called atmospheric deposition. This deposition occurs in both dry and wet forms. Dry deposition refers to pollutants settling to the earth much as dust settles in your home. During wet deposition, pollutants are literally washed from clouds and out of the air by rain, snow, sleet, hail, and fog before falling to earth. Some pollutants in the air combine with water vapor to form acids. Thus, wet deposition of such pollutants has come to be known as acid rain. But because snow, sleet, hail, mist, and fog are also involved, a more comprehensive term for acid rain is acid precipitation. What exactly is acid precipitation? The acidity of any solution is measured by its pH on a scale numbered from 0 to 14. A pH of 7 is neutral, neither acid nor alkaline. Solutions with a pH lower than 7 are considered acidic, while those greater than 7 are alkaline. Because the pH scale is logarithmic, a small difference in pH really means large differences in acidity. A change of 1 pH unit means a tenfold change in relative acidity. A pH of 4 is 10 times more concentrated than a pH of 5 and 100 times more concentrated than a pH of 6. Because atmospheric carbon dioxide reacts with water vapor to produce weak carbonic acids, pure rain has a natural pH of about 5.6. Precipitation with a pH lower than 5.6 is considered abnormally acidic. In much of the Northeast, precipitation now has an alarmingly low annual average pH of 4.0 to 4.5. Individual storm events have been recorded at pHs well below this. Winter snows also have low pH values, contributing accumulated heavy doses of acidity to lakes, ponds, and streams during spring snowmelts. Even cloud fog in the Vermont mountains has been shown to be 5 times more polluted than rain or snow. How does nature deal with this unnatural acidity? Though we do not yet have all the answers, we do know the following. Most surface waters are not as acidic as precipitation. Most waters have some capacity to neutralize acid input from wet and dry deposition. This neutralizing or buffering capacity varies depending on factors such as soil types, topography, bedrock geology, the acidity of precipitation, and the amount of precipitation. Because of its granitic bedrock geology and glacial soils, much of the northeast landscape is naturally low in buffering capacity. Many water bodies in this region thus have a limited capacity to cope with continued acid input. At some point, too much acid loading can overload a system's ability to neutralize acid input. The system then becomes very vulnerable, having lost its ability to resist pH changes. Alkalinity is a specific measurement of a water's buffering capacity and a reasonable indicator of vulnerability to acid precipitation. We can see in this graph of sampled Cape Cod ponds that once alkalinity or buffering capacity falls below 2 milligrams per liter, the pH drops very rapidly. Many lakes and ponds in the Northeast have experienced significant losses in alkalinity. In a 40-year period, these 3 remote New Hampshire ponds have experienced such alkalinity losses bringing them close to that point of dramatic pH decline. Dr. Paul Godfrey, director of the University of Massachusetts Water Resources Research Center, has found in a recent statewide survey of 1,173 water bodies that 82% of these lakes and streams are sensitive or vulnerable to additional acid input. In a separate study, Dr. Terry Haynes, biologist for the U.S. Fish and Wildlife Service in Orono, Maine, surveyed numerous lakes and streams throughout New England. This survey showed that more than half have poor capacity to neutralize acidity and are thus vulnerable to acidic deposition. Of these lakes, 8 to 10% are already critically acid, with pHs of 5 or less. Many of the lakes which are vulnerable to acid precipitation are also sources of public drinking water. The U.S. Drinking Water Standard calls for a minimum pH level of 6.5. Many raw water supplies in the Northeast fall near or below this. The Scituate Reservoir System, comprising about 10% of Rhode Island's fresh surface waters and the public water supply for about half the state, is low in buffering capacity and has pHs ranging from between 5.8 and 6.3. Water treatment is required to keep the pH up to drinking water standards. A 1982 survey of Massachusetts drinking water reservoirs shows an estimated 70% of them to be vulnerable to long-term acid deposition. Drinking water supplies low in pH corrode metal pipes and fixtures in the distribution systems and in homes. Most lead found in drinking water is a result of corrosion rather than naturally occurring lead in raw water. Such effects can be treated, but the costs are high. Several years ago, officials in the small town of Bennington, Vermont, found that many older homes in the town serviced with lead water pipes had high levels of lead in the tap water. The town's water supply is a small mountain stream in the Green Mountains. The stream was low in alkalinity, and its pH readings were often very low, some as low as 4.1. The combination of acidity and low alkalinity made the water corrosive, causing high lead levels in the tap water. To combat this problem, the town now keeps the pH level up by adding sodium bicarbonate and sodium hydroxide to the water each day at a cost of about $37,000 for chemicals alone each year. Lead pipes were used extensively in the water distribution systems of many older New England cities. In Boston, a 1974 sampling of tap water found high concentrations of lead. This water, coming from the Quabbin and Wachusett reservoirs, is now treated to prevent corrosion prior to entering the distribution system. Similar problems of corrosion have been found in water supply studies in New England and the Adirondack Mountains. To understand how atmospheric deposition affects our natural environment, consider the Earth to be composed of complex ecosystems with closely linked living and non-living components. What affects one part is eventually felt in other parts. Let's look first at aquatic ecosystems. pHs of 5 to 6 will eliminate many sensitive plant and animal species, crippling existing biological communities. Such disruption may reduce the total food resources available to fish and other animals. At pHs of 4.5 to 5, even the more acid-tolerant fish populations are eliminated. below pH 4.5, fish species cannot survive. Dr. Haynes comments on some of the effects critically acid waters are having on fish.
In these acid lakes, fish populations are either absent or are maintained by stocking. There is apparently no natural reproduction in lakes of this acidity. In the other lakes, the pH is not yet critically low, but the lakes are very low in alkalinity or buffering capacity and will not be able to resist acid precipitation for very long. If acidic precipitation continues at its present rate or increases, we could expect that these lakes will also become critically acid and will lose their fish populations sometime in the not-too-distant future.
In 1971, New Hampshire fishermen reported the absence of fish in remote trout ponds. Subsequent pond surveys yielded results indicating low pHs with no fish present in some ponds and missing age classes in other ponds. New York State fisheries workers observed some decline in fish populations in certain high-elevation Adirondack Mountain waters as early as the late 1950s. By the late 1960s, acid precipitation was incriminated as the probable culprit. Since that time, the problem has accelerated. In a 1979 study of 849 lakes and ponds, 1 out of 4 were found to be critically acidified. Dr. Carl Schofield, Senior Research Associate with the Department of Natural Resources at Cornell University, reports that many lakes in the Adirondack Mountains have undergone a reduction in pH over the last 2 decades, and that reproduction of fish has been substantially reduced. In a study of water chemistry and a fish survey of lakes above 2,000 feet, 85% of 111 waters with a surface pH less than 5 were found to be devoid of fish. New York State fisheries managers are attempting to provide some short-term solutions to counteract this complicated environmental problem. These stopgap measures include the experimental introduction of acid-tolerant strains of trout into some Adirondack lakes and the water neutralization process of liming. Liming can be effective in restoring lake water quality to the point where fish will once again survive. But most of the lakes sorely in need of liming are high-elevation, very remote bodies of water. These lakes have high flushing rates, and often it is simply not a practical management practice. It also tends to be very expensive. As we move from water to land, the impact of atmospheric deposition becomes even more complex. Dr. Hubert Vogelman, botanist at the University of Vermont, explains.
The environment is unbelievably complex. You have many different species of plants, many different kinds of microorganisms, algae, fungi, decomposers in the soil. The soil itself is a very complex component of the environment. And you have seasonal differences in precipitation and temperature. And when you start to try and sort out all of these factors, hundreds of factors, each impinging on each other, it becomes extremely difficult to show cause and effect relationships when you're dealing with a problem like acid rain. Someone once made the observation that ecosystems are not more complex than we think, they are more complex than we can think.
Dr. Christopher S. Cronin, botanist and ecologist at the University of Maine, and Dr. Carl Schofield have found that linkages between aquatic and terrestrial ecosystems are changing, in many instances due to the effects of acid precipitation. For example, it appears that aluminum, which would normally accumulate in the rusty-colored layer of this northern forest soil profile, is now remaining in solution and leaching on through the soil, making its way into groundwater and eventually into surface waters. Thus, in times of spring snowmelts, fish may suffer both from the acidity of the direct runoff and from the effects of high toxic levels of aluminum leached from the soil. Soil acts as a watershed's precipitation filter and is the nutrient source for forest vegetation. Dr. Steve Norton, geologist at the University of Maine, has found that acid precipitation can bring about significant changes in soil nutrients.
We attempted to assess the impact on soils of the variable quality of the rain falling in this large region. We sampled organic soil in spruce fir forests at 14 different localities. These soil samples were analyzed for their contained nutrients and metals. The data indicate that as one goes from the northeast to southwest, the amount of calcium diminishes in the organic layers in the soil. Inasmuch as calcium is an important nutrient for trees, this suggests that the nutrient reservoir in the soils is being altered and may be sufficiently affected in the future so as to diminish forest productivity.
Dr. Vogelman has observed dramatic changes in vegetation in his high elevation study area on Camel's Hump Mountain in Vermont, a location receiving consistently acidic precipitation.
In the 1960s, we began a study of mountain forests between 1,800 feet and 3,800 feet, and these represent the typical mountain forests that we find in New England. We established considerable baseline information. Recently, we went back and resurveyed the forests to see what kinds of changes have occurred in the last 15 years. And we found a dramatic change in the forests, particularly at high elevations. The big change was that red spruce, which is a dominant tree, has declined about 50%. That is, 50% of the individuals that were alive 15 years ago are dead today. We have not been able to identify a disease organism, so we are looking to environmental factors that may be responsible. Acid rain is one thing that we're looking at. We're also looking at heavy metals, lead, copper, zinc, which we know have accumulated in the last 15 years and are now incorporated in the forest soils.
Recent research in the Camel's Hump hardwood forest shows that sugar maple and beech have also declined 25 to 36% respectively. Man-made structures, particularly cultural property, historic buildings, and monuments, are not exempt from effects of atmospheric deposition. The once noble materials of antiquity, such as marble and bronze, are suffering from accelerated corrosion and weathering from acid rain. Arthur Beale, director of the Harvard University Art Museum Center for Conservation and Technical Studies, explains some of these effects.
Those of us that work in the area of the restoration of outdoor monuments are acutely aware of the problems of acid rain. We see it in our work every day, and we're being called upon with greater frequency to treat monuments such as the Shaw Memorial, which is in Boston. It looks very much now as it did when it was created at the turn of the century. But just a few years ago, it was suffering from the ravages of acid rain, especially the exposed elements, the Shaw and the Horse, where there are disfiguring patterns of copper sulfates and sulfides from sulfuric acid runoff, and deep etching, disfigurement, and loss of sculptural detail. This is characteristic of what we see with bronze statuary. The problems are very similar and even more serious with monuments made of limestone and marble, which are particularly sensitive to acids, particularly sulfuric acid again. The cementing material of the stone is dissolved away and the stone eventually crumbles. And then with building materials, the materials of historic properties, which similarly are often masonry, limestone, sandstone, and marble, the very structure of the building is affected. Here we haven't even got stopgap measures. We only have experimental procedures at the moment. The rate of deterioration is really alarming, and we can measure it by looking at dated tombstones and erosion of grave markers. It's a race against time as far as the conservators are concerned. Our measures are futile unless the environment is cleaned up. In dealing with our irreplaceable cultural property in this hostile outdoor environment, costs become irrelevant. The loss of these things is forever.
The economic impact of atmospheric pollution in relation to the maintenance of painted building exteriors on historic and contemporary structures is enormous. In the Boston metropolitan area alone, it has been estimated to be in excess of $30 million each year. The issue of acid precipitation has both direct and indirect effects on human health. As we have already discussed, impurities in our drinking water pose a threat to our health and well-being. It has also been discovered that the deposition of metals and other airborne contaminants into surface waters has in some instances resulted in an accumulation of such pollutants in fish. While they may not be toxic to fish, they may accumulate as contaminants in fish and thus become unsuitable for human consumption. There is no apparent cause for concern over direct damage to the skin or gastrointestinal tract from acid precipitation. However, the inhalation of high levels of respirable air pollutants, such as sulfates and other fine particles and aerosols, may produce respiratory and other internal disease. Even low-level exposure to these substances can prove harmful to human health. Sulfates are strongly associated with cancer deaths, as well as heart, lung, and circulatory failure. The fine sulfate particles are carried well down into the respiratory system when inhaled. According to a study published in 1979 by Drs. Robert Mendelsohn and Guy Orcutt, sulfates account for as many as 185,000 deaths in the United States per year. The study also noted that the probability of dying from air pollution in the north central and northeastern regions of the U.S. is about twice as high as the rest of the country. But where is this polluted air coming from? The major components of acid precipitation are nitric and sulfuric acid. Both sulfuric and nitric acids can be traced primarily to sulfur oxide and nitrogen oxide gases emitted into the air. By far the most significant amounts of air pollutants come from man-made sources, such as power plants, industrial processes, and cars and trucks. Emissions from these sources react chemically with moisture and sunlight to form acids. Other chemical compounds and heavy metals are also involved. All these pollutants become part of the air masses circulating in the atmosphere and eventually fall back to Earth at varying rates and under a variety of atmospheric and climatic conditions. The industrial Midwest is responsible for more than half of the sulfur dioxide emissions east of the Mississippi. The state of Ohio alone produces almost 2 times more tons of sulfur oxides per day than all of the 8 Northeast states put together. Air pollutants from these distant sources contribute to poor air quality in the Northeast environment. In Connecticut, as much as 70% of airborne particulates, 25% of which are sulfates and nitrates, are attributable to pollution sources from states to the south and west. Several thousand tons of sulfur oxides, sulfates, and nitrates pass over or are deposited on Connecticut each year. And in this manner, our poor air quality has even affected our visibility. Rich Poirot, Air Quality Planner, Vermont Agency of Environmental Conservation, explains.
Aside from the weather, sulfate particulate in the atmosphere is the single most important factor affecting visibility in the Northeast. Sulfate is a terrific light scatterer, and its ability to scatter light is greatly enhanced by a combined effect of high relative humidity in the region. Here we have the view from the top of Mount Mansfield, Vermont's highest peak, on September 12, 1980, a day when sulfate concentrations in the air were very, very low, less than 5 micrograms per cubic meter. In the distance we can see Mount Washington about 80 miles away. When we trace the trajectories or the paths that the air traveled prior to arriving in northern Vermont on September 12th, we find that this air came down from northern Canada, passed over regions of relatively low sulfur emission density. Unfortunately, all of our air does not come from this direction. Consider the trajectories of air arriving in northern Vermont on June 26, 1980. This air previously passed over regions of very high sulfur emission density, in this case the Ohio River Valley. By the time it reached northern Vermont, sulfate concentrations in this air mass were in excess of 30 micrograms per cubic meter. Now, if you were to climb Mount Mansfield and try and look at Mount Washington through 30 micrograms per cubic meter of sulfate, you're going to be disappointed.
Summertime sulfate episodes are becoming more frequent in the Northeast. During the past decade, summer has become the haziest or dirtiest season of the year. This has a direct bearing on tourism, which is vital to New England's economy. These visibility trends carry serious economic implications for this region. When considering the effects of airborne pollutants on lakes, reservoirs, groundwater, plant life, and people, we realize that we face a phenomenon not easily observable and not necessarily short-term. In fact, many of these effects may be irreversible. There remains a serious gap in our knowledge and understanding of the long-term effects of atmospheric deposition. There is no simple way to determine the extent of damages and losses being suffered in the Northeast. However, the technology to reduce emissions from power plants and industry does exist. Its use has been limited for economic reasons. It is expensive to reduce emissions at their sources, but this is ultimately the way the problem must be approached. The Federal Clean Air Act has guidelines and standards which new sources of emissions must follow. But state air pollution control directors in the Northeast are frustrated by two major aspects of the long-range pollutant transport problem which are not adequately addressed by the Clean Air Act. First, there are tremendous inequities in federally approved state standards for emission rates from older pollution sources in different regions of the country. Midwestern states are allowed higher pollution emission rates than the Northeast. Second, it is very difficult to comply with the air quality standards in the Northeast when so much of the pollution is transported into the region from other regions, pollutants over which northeastern states have absolutely no control. In addressing the problem of atmospheric deposition, we are faced with making trade-offs between the economy and the environment. And it need not, and indeed should not, be a question of either or. We are not alone in facing this dilemma. Between 1970 and 1975, the Japanese cut their total sulfur dioxide emissions by half, primarily by retrofitting existing power plants with emission controls. It is important to note that this aggressive pollution reduction policy was fully endorsed by all segments of society, including industrialists. During those same 6 years, Japan more than doubled its generation of electricity to fuel its expanding economy. More recently, recognizing the damage to forest productivity from acid rain, West Germany has initiated a program to reduce sulfur dioxide emissions by 50%. Switzerland has also signed a compact with West Germany recognizing the need to take steps to reduce sulfur dioxide emissions significantly. Although much of Canada's acid rain-related damage is caused by emissions originating in the United States, the Canadians are currently proceeding to reduce sulfur dioxide emissions in eastern Canada by 25%, and will make reductions of up to 50% if the U.S. commits to similar reductions. In the U.S., Northeast and Upper Midwest states have entered into mutual agreements with Canadian provinces to collaborate on scientific research and to cooperate in developing emission control strategies. What will we as a nation choose to do? Without a healthy environment, we cannot have a truly healthy economy. Yet we can have both. The question of who will bear the burden of cleanup costs can be resolved equitably. We need not settle for poor health, barren lakes, hazy views, and threatened water supplies, forests, and crops. While continued research is essential, it is not enough at this point. Most scientists are in agreement that enough is already known about the alarming consequences of atmospheric deposition to act now, and that the most effective form of action is to reduce emissions at their sources. The problem will not be resolved with stopgaps and bandages. It must be addressed in its entirety, with a view toward now and tomorrow. A concerned and aware public can promote innovative approaches toward resolving problems such as these. We can knowledgeably demand that our legislators support and enact laws which are protective of all of us and our environment.
This acid precipitation problem is one of the biggest environmental problems that we face in the coming decade, if not the biggest one. And I say that because it is so widespread. It isn't confined to state or region. It's a bigger problem because of the fact that it's insidious. It's silent, it's invisible, and to the casual observer, it isn't happening. But it's very well documented that it is happening, and with some very severe consequences.